In a modern cardiovascular hybrid operating room, patient survival is a routine expectation. Look at the structural mandates for this space. The architectural checklists demand lead-lined walls, doors, and window frames, paired with a minimum of 25 dedicated air changes per hour. This floor plan shows how the suite is physically isolated from the rest of the hospital. Semi-restricted corridors and dedicated clean cores lock the surgical environment away from general traffic to maintain strict infection control. But while architectural isolation protects the patient from external pathogens, the actual clinical decisions happen behind the glass. The surgical team relies entirely on the diagnostic monitors mounted in the control room. Because the surgeons cannot look directly inside the patient's vascular system, their diagnosis depends entirely on the mathematical perfection of the digital display. During an interventional procedure, the clinical team's direct line of sight is replaced by a high-definition video feed, tracking the contrast dye as it moves through the patient's arteries. If the image routing introduces even a minor visual artifact, or if the monitor fails to render a subtle shadow, the physician makes a misdiagnosis. To understand how hospitals prevent those fatal rendering errors, we have to reverse engineer the clinical data chain, starting at the pixels on the screen and working backward to the physical hardware. That pathway is built on 3 distinct layers of engineering: display calibration, network routing, and modality maintenance. A life-saving diagnosis relies completely on an unbroken chain of data integrity. The final rendering point is the diagnostic monitor. Here, strict perceptual precision is required to accurately interpret clinical data. Commercial off-the-shelf displays cannot process medical data safely because they rely on 8-bit processing, which maxes out at exactly 256 shades of gray. This diagram compares standard rendering with medical-grade rendering. On the left, an 8-bit gradient exhibits harsh, stepped banding. On the right, medical-grade displays utilize 12-bit to 16-bit processing to render thousands of continuous grayscale transitions. When a scan is overlaid, critical microstructures hide inside the crushed bands of the 8-bit side. The expanded 12-bit depth preserves the subtle density differences between soft tissue and contrast dye. That expanded processing depth prevents a lethal pathology from vanishing into a crushed black level on the screen. That pixel-level precision is governed by a mathematical standard known as the DICOM Grayscale Standard Display Function, or GSDF. This graph illustrates the standard. It plots digital image values against luminance output, forming a curve mapped directly to the nonlinear contrast sensitivity of the human eye. The system runs incoming data through a 14-bit lookup table, forcing the display output to obey a strict gamma 2.2 relationship. This guarantees that an image looks identical on any calibrated workstation in the facility. Maintaining that strict curve requires immediate hardware intervention. LED backlights degrade over time, so internal sensors continuously modulate the backlight voltage to stabilize luminance at 1,000 candelas per square meter. DICOM calibration is a continuous, active mechanical process combating the physical decay of the display. If we trace that calibrated signal backward from the monitor and into the wall, we enter the routing architecture. The digital nervous system of the operating room is the Interventional Information Management Suite. Because diagnostic monitors operate at up to 8 megapixels, their massive data output must travel across dedicated fiber optic cables to preserve the native image resolution without introducing latency. Fiber optics also transmit data using light. This isolates the data stream from the intense electromagnetic interference generated by adjacent equipment, like MRI scanners. A closed fiber architecture protects the purity of the raw diagnostic signal from the ambient electrical noise of the hospital. But this high-speed, pristine network cannot operate in isolation. It eventually has to connect to the older IT infrastructure of the broader hospital. This schematic maps out how the transition happens. Modern high-bandwidth nodes pass data through rigid translation hardware, like 3D SDI connections and fiber extenders, to step down the signal for the legacy network grid. The ultimate destination for that translated data is the PACS, the Picture Archiving and Communication System. The archive locks the image data to a specific text file. The PACS permanently pairs the raw DICOM pixels with the patient's demographics, the acquisition parameters, and the institutional identifiers. A perfect scan has zero clinical value if it cannot be correctly translated, routed, and archived into the patient's permanent record. At the very beginning of the network path sit the physical imaging modalities, the CT scanners, fluoroscopy suites, and ultrasound probes generating the raw data. This dashboard demonstrates the strict daily maintenance checks for a CT scanner. Before a patient enters the room, engineers execute tube warm-up protocols to protect the X-ray filament and run water phantom scans to verify the Hounsfield units stay within a strict tolerance. For digital radiography and fluoroscopy suites, the protocol requires regular flat field calibrations to identify and map out detector dead pixels and correct gain calibration drift. Ultrasound probes require a completely different approach. Technicians perform visual inspections for cracked transducer lenses and measure electrical leakage current to protect patients during endocavitary exams. Missing one of these preventative tasks allows a minor calibration drift to escalate. On average, a hardware failure at this level results in 4.6 days of catastrophic unscheduled clinical downtime. The life cycle of a clinical image is highly structured and deeply interdependent. It begins with the mechanical precision and daily quality assurance of the physical scanners. It relies on high-bandwidth fiber optic routing and complex hardware translation to reach the legacy hospital archive. And it concludes on mathematically precise, DICOM-compliant diagnostic monitor that actively fights its own physical degradation. A failure at any single point in this triad instantly compromises the validity of the entire system. The people holding this architecture together are the clinical engineers and biomedical equipment technicians. Their daily calibration schedules and network optimizations are an active, ongoing war against system entropy. In the cardiovascular lab, equipment uptime is a prerequisite for patient survival. The rigorous enforcement of this engineering lifecycle is the only reason clinicians can safely trust their screens